Introduction to IEEE Standard 754 Floating Point Numbers. Hello, everyone. We're going to look into floating point numbers and more specifically IEEE Standard 754. Floating point numbers are crucial in especially scientific computing and numerical analysis, allowing us to represent real numbers in a way that can be easily manipulated by computers. So the IEEE standard provides a standardized method for representing and working with these numbers, ensuring consistency and accuracy across different computing systems. Historical context. So before the standard IEEE standard was developed, there were significant inconsistencies in floating point arithmetic across different computer systems. So different manufacturers had their own ways of representing and handling floating point numbers, and this led to varying results and numerous challenges in scientific and engineering computations. Thus, the IEEE 754 standard, introduced in 1985, addressed these issues by providing a unified approach, which has since become the foundation for floating point arithmetic in modern computing. Basic concepts. So in order to understand floating point numbers, we first need to distinguish them from fixed point numbers. Fixed point numbers have a fixed number of digits after the decimal point, which limits their range and precision. In contrast, floating point numbers use a scientific notation-like representation with three main components: the sign, exponent, and significand or mantissa, to allow them to represent a much wider range of values with greater precision. And we can see this Python example. This shows the difference between fixed point and floating point representation. And fixed point number is an integer, while floating point number, this variable, is a floating point number, which is capable of representing fractional values. So the IEEE 754 standard defines several formats for floating point numbers, but the most commonly used are single precision and double precision. Single precision uses 32 bits, making it more memory efficient, while double precision uses 64 bits, providing greater precision and range. So understanding these formats is really important for working with floating point numbers in various applications. And if we look at this Python example, it uses Python's struct module to demonstrate how a floating point number is packed into binary format and then unpacked. So we can see that struct pack and struct unpack are used to convert the floating point number into its single and double precision binary formats and back to floating point values. Structure of IEEE 754 floating point numbers. So let's break down the structure of these numbers. In single precision, we have 1 bit for the sign, 8 bits for the exponent, and 23 bits for the significand or mantissa. And for double precision, similar to 32-bit single precision number, there is 1 bit for the sign, and 3 more bits are allocated to exponents. So there are 11 bits for the exponent, and then 52 bits for the significand or mantissa. So this structure allows us to represent numbers in a standardized way, facilitating accurate and consistent computation. And here we have Python code, and we have this function called float2bin, which is a function that to display binary representation of floating point numbers. So this the binary string is split into the sign bit, exponent bit, and significand bit to show the structure. Sign bit. So the sign bit is the simplest component of a floating point number. It determines whether the number is positive or negative. A sign bit of 0 indicates a positive number, while a sign bit of 1 indicates a negative number. So this straightforward representation helps maintain consistency in arithmetic operations. And if we look at this Python code, we have a function called extract sign bit, and this function extracts the sign bit from the binary representation of a floating point number. And this example uses a negative number to demonstrate that the sign bit is 1 for negative numbers. Exponent. So the exponent field is where things get interesting. It uses a biasing technique to represent both positive and negative components. So in single precision, for 32 bits, the exponent bias is 127. It means that an exponent value of 127 represents the actual exponent of 0. In double precision, the bias is 1023. It means that actual exponent is calculated by subtracting the bias from the stored exponent value. This approach helps efficiently encode a wide range of values. And if we look at Python code example, we have extract exponent function, and this function extracts the exponent bit from the binary representation of a floating point number and calculates the actual exponent value by subtracting the bias. And here we're dealing with 32-bit single precision values, so we're subtracting 127. So example number is declared and stored in num. And if we call extract exponent, then we will be able to get exponent bits and exponent value. Significant or mantissa represents the significant digits of the floating point number. So in normalized form, there is an implicit leading one, which is not stored but assumed. This allows us to use all available bits to store the fractional part, thus maximizing precision. The value represented by the significand is 1 plus the fractional part stored in the bits. So if we look at this Python code, we have extract significand, and this function extracts the significant bits from the binary representation of a floating point number. And the example shows how the fractional part of the number is stored in the significand. Special values, which is 0. So in the IEEE 754 standard, both positive 0 and negative 0 are represented. You might find this to be odd, but this can be useful in certain mathematical context. So for example, positive 0 and negative 0 can behave differently in certain operations, such as division, where dividing by positive 0 yields positive infinity, and dividing by negative 0 yields negative infinity. And in Python, you can see that through this example that positive 0 and negative 0 are represented. So it shows that while positive and negative 0 are conceptually different, they are considered equal in numerical comparisons. Next is infinity. So the IEEE 754 standard also defines positive and negative infinity. And these values are used to represent results that exceed the largest representable number. It is a condition known as overflow. So positive infinity results from operations like dividing a positive number by 0, while negative infinity results from dividing a negative number by 0. So by having these special values, it helps handle extreme cases in a consistent manner. And here, if you look at this Python example, it shows you how to represent positive and negative infinity in Python. And these values are used to represent overflow conditions and floating point arithmetic. Next, nan, or not a number. So nan, or not a number, represents undefined or unrepresented values. For instance, the result of dividing 0 by 0, or taking the square root of a negative number, is nan, or not a number. And this not a number are useful for error handling, allowing computations to continue even when encountering undefined operations. So there are two types of NANDs. One is quiet NANDs and signaling. Another is signaling NANDs, which differ in how they propagate and signal exceptions. And here, if you look at example, it demonstrates the representation and behavior of NaN in Python. So it shows that NaN is not equal to itself, which is a unique property used to indicate undefined or unrepresentable values. Denormalized numbers, this is another special value. So denormalized numbers are used when the exponent field is all zeros. In this case, the implicit leading one is replaced with a zero, allowing the representation of numbers closer to zero than normalized numbers. So while this increases the range of representable values, it comes at the cost of precision. So denormalized numbers are particularly important for maintaining gradual underflow, where numbers close to zero are represented more accurately. So here, if you look at this example, it shows the smallest positive denormalized number in single precision. And we're using the NumPy library to handle this number. And denormalized numbers allow representation of values closer to zero than normalized numbers. Rounding modes. So IEEE 754 specifies several rounding modes to handle situations where the exact result of an arithmetic operation cannot be represented. So the default mode is round to nearest, which rounds to the nearest representable value. Other modes include round toward zero and round toward positive infinity and round toward negative infinity. And each mode has different implications for precision and accuracy, and the choice of rounding mode can affect the result of computations. And if we look at this Python example, this example demonstrates different rounding modes using Python's decimal module. And each mode shows how the number 3.14159 is rounded to 3 decimal places, illustrating the effects of each rounding strategy. So I highly encourage you to try this example. If you actually try this, the round to nearest should end up with 3.142, since 3.14159 is closer to 3.142 than 3.141. Round towards zero should give you 3.141 because we are truncating the digits after the third decimal place, and round toward positive infinity should give you 3.142 because rounding up regardless of the digit, because we're rounding up regardless of the digit after the third decimal place. and round toward negative infinity should give you 3.141 because we're rounding down regardless of the digit after the third decimal place. Basic arithmetic operations, such as addition, subtraction, multiplication, and division, they can be performed according to specific rules in the IEEE 754 standard. The details of these rules are out of scope for this lecture, but just know that these rules ensure consistency and precision across different platforms. Since Python follows this, we can just see that basic arithmetic operations on floating point numbers is as simple as this example shown here. Handling edge cases. So edge cases such as overflow, underflow, cancellation can significantly impact the accuracy and reliability of computations. Overflow occurs when a result exceeds the largest representable number, thus leading to infinity. And underflow happens when a result is smaller than the smallest representable number, leading to denormalized numbers or zero. And cancellation occurs when subtracting nearly equal numbers, causing significant precision loss. So being aware of these edge cases helps in, especially if you are dealing with numerical algorithms. And here is a Python example that demonstrates edge cases. And the first one shows overflow when a number exceeds the largest representable value. And here is underflow example. We are multiplying small number by small number. So this number is smaller than the smallest representable value. And here we are subtracting nearly equal numbers, and this results in significant precision loss. Precision and accuracy. So floating point representation involves trade-offs between range and precision. For example, adding a very small number to a very large number may result in no change due to precision limitations imposed by IEEE 754 floating point number. And this loss of precision can have significant consequences when doing scientific and engineering computations. So understanding these limitations is crucial for ensuring accurate results. And we have Python example to demonstrate this precision loss in floating point arithmetic. So we have very large number and very small number. And adding a very large number and small number, and then subtracting the large number will give you results that has a loss in precision. Highly encourage you to try this out. Performance considerations. So most modern processors have hardware support for IEEE 754 operations, thus making floating point arithmetic fast and efficient. However, performance considerations such as the choice between single and double precision can impact both the speed and accuracy of computations. If you're dealing with performance critical applications, it is important to balance the need for precision with the available computation resources. And here we have a code example that compares the performance of single and double precision floating point arithmetics. And we can see that it runs a loop of multiplication on single precision and double precision numbers and measure the time taken for each. And I encourage you to try this out to see which one performs better on your machine. Common pitfalls and best practices. In order to avoid precision errors and ensure numerical stability, it is important to follow best practices. You want to avoid subtracting nearly equal numbers to prevent cancellation errors. And you want to be cautious with comparison due to precision limitation. So use higher precision formats if necessary for critical calculations. And following these practices helps maintain the accuracy and reliability of numerical computations. Conclusion. So the IEEE 754 standard provides a consistent and accurate method for representing and working with floating point numbers. So understanding the structure, special cases, and arithmetic operations is crucial for scientific computing and numerical analysis. This is it for the lecture. Thank you everyone for listening.